Good morning. This is Mike Mazzarese with AST. It's 9:30 here in the Mountain Time Zone. So we're getting ready to start here. We are going to wait 1 minute though, and we have a bunch of folks that are still logging in. So we're going to get started in about 1 minute or so. So thank you. All right. Well, hello everyone. Thank you for joining us today, in whatever time zone you are currently in. The Chinese calendar says it's the year of the rat. However, I would argue in our industry this year, it's the year of the webinar. I know that you've all been attending more of these than you probably ever have in your career. And so we all thank you from my company, AST, RPI, and the RPI group. So we thank you for taking time out of your busy schedules to join us this morning. Just a few notes here before we get started. I've already gotten one question about a copy of the slides. Yes, we can make the slides available at the end of the presentation. This is also being recorded. And so if you have to bail early, or if you'd like to send a copy to a colleague, those will be available. They usually post within a week on the RPI website. And down at the bottom of the slide that you're seeing currently, bob@trapandtreat.com if you're interested to get a copy of the slides. We will have questions at the end, so I'm going to MC the presentation today. So Scott Nolan is the presenter. I will be monitoring the questions that come in, so you can use the question box there on your slide bar and send those to me. I'll be monitoring those as we go through the presentation, and we'll cover those at the end. If for some reason we don't get to them all, we can go ahead and follow up with you afterwards. And one last note. So this is, we ran, I'm not sure if some of you attended our spring series. This is our fall winter series. And so this is the first of 6 presentations over the next, between now and Christmas. We've got 3 here in November before we get to the Thanksgiving holiday, and then 3 in early December leading up to the Christmas holiday. So if you would like to register for any of these, again, you can hit up Bob Elliott at bob@trapandtreat.com. So Scott, so our presentation today is by Scott Nolan. So he's a president RPI. He's the gentleman that developed the trap and treat technologies that will be covered today. And he's going to talk about using activated carbon as a remedial platform for the last almost 2 decades. So Scott, I'll turn it over to you.
Thank you very much, Mike. Good morning to everyone. Thanks for joining us. If I can figure out how to operate my system, I'll be doing good. Anyway, RPI has been putting carbon into the ground for about 19 years. And the picture that you're looking at is from the very early days of our efforts in commercializing the use of activated carbon in remediation. And as it turns out, activated carbon, powdered activated carbon in particular, is when you put it in a tank with water, it doesn't sink, even though the density of carbon is well above water, it floats. And so what you're seeing here is a picture of, it was a mixed tank long time ago, and the fellows out here put 50, 100 pounds of powdered carbon into a tank, and then they put a mixer down in the tank and turned it on. So the first thing that happened is there was, vortex down, and the carbon kind of got sucked down in the vortex, and then literally 50 pounds of carbon just came bouncing out of the tank. And well, you could see what the result was. Since that time, we've come an awfully long ways. And one of the takeaways from this early time was we learned about eductors, and eductors are now commonly used to actually get material into the tanks and wet the carbon, because it turns out carbon is a little bit more difficult to wet. So if you were to ask me, what's the single most important thing that has led RPI Group to the success that we've enjoyed over the years? I would have to say it's the lab at RPI, and here's why. Injections are surgical in nature. Every injection targets some volume in the subsurface of contaminated formation, and the size of that volume is really dictated by the grid spacing between injection points, the vertical spacing between injections, but you're targeting some amount of volume in the subsurface. And that volume in the subsurface has some amount of mass in it. And so one of the things that's really important when it comes to in situ remediation is understanding that vertical change in contamination on sites as a function of location within the contaminated plume. This data is some real data from a site that was here in Denver, Colorado, and it's TCE concentrations, and as you can see, in micrograms per kilogram as a function of depth in meters, and also the lithological setting. So you can see it's a depositional environment. The really cool thing about this data is you can see how rapidly the concentration is increasing as a function of depth. And the highest concentration we're seeing here is 25,000, over 25,000 ppm. And if you notice, that's in a seam of silt that's about 1/4 of an inch thick. 25,000 ppm, as we all know, that's 2.5% by weight. The highest concentration that we actually saw out on this site was 54,000. But the point of this slide is that concentrations can change very rapidly, and you can have extremely high concentrations in very localized environments. And if you don't understand, if you don't know that this exists, you could clean up all of the contamination above that silt zone and all the contamination below that. And this site was originally earmarked for oxidants. They were going to inject potassium permanganate. But if you didn't understand that this existed, you'd be injecting permanganate for a really long time, as I'm sure everyone out there can understand. And so how does this relate back to success we've had? Well, the lab, during RDC work, we take a lot of soil samples, and my hat's off to the geologists who actually teased this out and took those thin slices and submitted them to the lab for analysis. So having set the stage for at least one of the, I think, most important aspects of in situ remediation is understanding this distribution. Petroleum hydrocarbons are a little bit more forgiving, but this kind of behavior in chlorinated solvents is not uncommon. Anyway, now let's move on and talk about carbon. Over the years, I mean, activated carbon is not new. It's been around for decades. And over the years, the industry has really developed rules of thumb regarding activated carbon. Things like all carbons are the same. I can tell you that all carbons are not the same. So coconut is different than bituminous coal. Bituminous coal is different from lignite, and that's different from wood. All these carbons have different properties. And as you can see, the properties of the activated carbons that you get from these different things are dictated by the material itself, the ash impurities, the density, the pore structure of the material. Coconut shell is quite different from bituminous coal and also from wood if you start looking at it underneath a microscope. So this is an important thing to keep in mind. And I've seen statements like that even in, for example, an EPA white paper where it basically said all carbons are the same, and they're not. One of the really important things about activated carbon is just the idea between virgin carbon and reactivated carbon. And it's one of the real powers of carbon that's been taken advantage of in the marketplace over the years, is that its ability to be reactivated. So once it's spent and used in like pump and treat systems, that's been going on for a long time, you can send it back and have it reactivated. So the difference between these things, virgin carbons are brand new. They're newly manufactured. They've never been used for anything from raw materials such as coal. RPI uses a high-grade bituminous coal to manufacture all of its products, and all of our products are based on virgin carbons. There is a whole other segment, though, in the activated carbon industry, and that's the react carbons. And essentially, you have two different marketplaces. You have the drinking water segment, and then you have wastewater. Drinking water carbons are really closely managed. These are the carbons that are utilized by many municipalities all over the country. So those are managed very closely to make sure that nothing bad gets mixed in with those. They're reactivated, and very often they're just sold right back to the original municipality where they came from. So the housekeeping on those guys is really closely managed. Where on the wastewater carbon side, that housekeeping is very poor. So you get carbons coming from all kinds of different places, from the plating industry, from various other manufacturing industries, and they all get kind of put together. There's not a lot of housekeeping that goes on with that. So there's a very high potential that reactivated carbons can contain contaminants like heavy metals. The reactivation process is going to eliminate any organic contaminants, but metals still are potentially present. So the takeaway from this would be that don't ever use reactivated carbons for in situ remediation because of this potential. So another feature of activated carbon, and this is, people tend to think that once something is absorbed to carbon, it's just stuck there forever. It's not true. This is really a thermodynamic process, and there's a heat of absorption for all of these things. So and rollover is a process whereby one thing that's been absorbed to carbon can now be kicked off or displaced by something else. And to illustrate this, we did an experiment in the lab where we set up two vials, and we exposed carbon in one vial to 2000 ppm xylene, and in the other was 100 ppm vinyl chloride. We used pretty high concentrations just so that we could illustrate this fact in a very short period of time. So at equilibrium, we let these things mix for a 24-hour period. You could see what our equilibrium concentration was based on whatever the dose of carbon that was employed in the test. We had 1.4 ppm left in the water and 2.42 ppm of vinyl chloride left in that one. So then what we did is we came along and we spiked the vinyl chloride vial with 2000 ppm of xylene. And now you can see what the results were. In a very short period of time, the vinyl chloride concentration is now increasing. The xylene, which has a higher heat of absorption, is kicking the vinyl chloride off of the carbon. After 24 hours, you can see we're up to 16, and things are still changing. So why is this important? The fact that these things aren't stuck on there all the time has tremendous impacts out in the industry. What it means is that something that's on, when you inject carbon in the ground, if you don't have a viable degradation mechanism in place to degrade the carbon, to degrade the contaminants that are absorbed to the carbon, you're going to have problems in the future. This really has dire implications when it comes to PFAS compounds. And there are a lot of people out there that are promoting the use of activated carbons to treat PFAS. And this is a big mistake. The heat of absorption for PFAS compounds is pretty low. And so initially, when you put the carbon in the ground, things might look very good. You're absorbing a lot of these compounds, but then over time, other contaminants that are in the water begin to displace those things. And so then you'll have ultimately what you create is a brand new source of PFAS compounds in the ground. Not only do we communicate this to people, but RPI has taken the position from day one none of our products to date have ever been used on a PFAS site because of this problem, and they never will be. So this is a very important concept to just not forget about. So here's another aspect of activated carbon, and it has to do with absorption capacity. And this also comes back to another one of those rules of thumb, where activated carbon can in general pick up about 15 to 20% by weight of other materials, be it petroleum hydrocarbons, chlorinated solvents, whatnot. So here I'm showing you what the difference in the absorption capacities are between a couple of very common compounds. So you can see here some data for benzene at equilibrium. If I have a concentration of 10 ppm, I end up with about 40 milligrams of benzene per gram carbon. But you can see it's a function and a strong function of concentration. And the equilibrium absorption capacity changes dramatically depending on what the dissolved phase concentration is in the water. Then when you compare benzene, the absorption capacity, to ethyl benzene, you can see we're basically an order of magnitude different here at 10, and the differences are quite stark. So again, this needs to be kept in mind. The performance of activated carbon is strongly a function of the contaminant that's present and the concentration it's being exposed to in the subsurface. So we have done a lot of lab work here at RPI, and we conducted a test with diesel fuel. And diesel fuel, as everyone knows, is not terribly soluble in water. So what we did is we actually did some experimentation to look at absorption capacity, kind of through that lens of the slide I just showed a minute ago. And we used a couple of different carbons, the standard carbon that we get from Calgon, and then also a wood-based carbon. And what we did is we put some carbon together in a bottle of water, and then we added diesel fuel, and then we mixed it for a period of time, and then carefully separated all that out, and then measured the amount of material that had been absorbed at saturation on the carbon. So you can see carbons are quite different, and the wood-based carbon, although originally I thought that it would pick up a lot more material, it didn't. It performed much more poorly than the activated carbon that the bituminous coal-based carbon that RPI uses in its products. So this tends to show that that rule of thumb of about 15% total absorption is incorrect, and certainly doesn't apply across the board. But the more important thing associated with this is not the absorption capacity. It has to do with degradation of things that are absorbed into the carbon. And from the very beginning, RPI has always said the carbon cleans the groundwater, the bugs clean the carbon. It's kind of a catchy phrase. The carbon cleans groundwater, the bugs clean the carbon. Industry thought about that. Industry came back and said the bugs are too big. They can't fit into the pore structure of the activated carbon. And they're correct. However, there's ways for bugs to get down inside the activated carbon and be able to get at those things. So coming back to this bench test on diesel fuel that we conducted, some of the things that you can see are quite visible when it comes to some of these tests. So these are some of the test files from a diesel bench that we put together, and you can see the various different colors. These colors are really generated because of trace metals that are put in there as nutrients. So some things are clearly visible. So for example, the yellow tinted vials really, I'm pretty sure that that's due to iron. That was, the valence state was changed in the iron as a consequence of the biological activity of the diesel. And what we did is we used that pre-diesel loaded carbon in this test. Then the pink vials are probably stemming from either, for the moment, my mind just went blank, but it could be permanganate, although I don't think we put permanganate in there. shoot. Anyway, I'll move on. But the color here is due to one of the metals that we added in there. So you can see that there's obviously some very large differences between what's going on in these different vials biologically. Love this slide. This is again from that diesel bench. And it shows the extensive biological activity that's going on, and the carbon that was in there is encased in this glob of material. You can see there's a lot of activity going on. The consistency of this was almost like egg drop soup. So this is just really a cool slide that shows biofilm formation, gas generation from the degradation of the diesel fuel that was actually absorbed into the pore structure of the carbon. So clearly these things are bioavailable, even though they are adsorbed onto the carbon. I'm going to spend a little bit of time on this slide. This is again related back to the diesel bench that you saw the vials from. So here is our preloaded carbon, and it contained just over 180 milligrams of total diesel fuel on the dose of carbon that we put in. And then what we did is we tracked the degradation of the total diesel fuel in the systems over time. And the really interesting thing about this line is it's pretty much linear. All of the normal kinetic models that I think of, like first order kinetics, they're not straight lines. This one, though, is really like zero order kinetics. And it's telling us something that's very important. The thing that I believe it's telling us is that there's a direct relationship between the platform of the activated carbon and the kinetic rates of degradation. This is like a massive stage. The larger the stage, the more rapid the degradation. The straight line fit on this curve, you can see here, shows not only this is the intercept, this is where we started at approximately 180, and the slope of the line is related to the kinetic rate of degradation. You can see the correlation is pretty decent. So this is a really important kind of a relationship, because what it suggests is that activated carbon can really help with natural source zone depletion. And this graph, a lot of people may recognize. This is out of a LNAPL guidance document from ITRC. And on the one side here, you can see this is the depth to the anaerobic interface between where we're aerobic and where we're anaerobic. And then you have a number of lines across here with the hydrocarbon degradation rate on the x-axis. So these different lines correspond to different lithologies. This blue line here is clay, and this line down way over here to the right is gravel. So you can see obviously that these rates of degradation are going to be quite different depending on what kind of lithological settings. But if you kind of look around at, just what's the average kind of site look like, what kind of degradation rates might you see, the interface between the anaerobic and aerobic location would be maybe between 10 and 20 feet. A lot of sites fit into that area. So we're probably looking at right around in this area. So we had been involved in a test out in Texas, and I'm going to share some of the data from that site. And we're going to keep in mind the degradation rate in here, just looking at this mnemonic graph of maybe being around 2 grams per meter squared day, somewhere right in here in the middle. So at this site, and it was in Texas, we actually took advantage of the chemistry that I was showing you some of the data of in the colored vials a couple of slides ago. And we took that approach and we applied it out on a large condensate site out in Texas. And when you take a look at the removal rate that we got from the ITRC graphs, and then apply that across the area of the plume that we were treating on this site in Texas, and you can see that this becomes about 730 grams of free phase per meter squared year on this particular site. The mass removal rate that was estimated from the condensate site was over 5,000. Now, this is the same technology that was applied in that diesel bench test that I was showing you earlier in terms of the degradation and some of the things that we observed during that bench test. So what this says is that the use of activated carbon in these LNAPL sites really enhances the rate of natural source zone depletion. There's a key role to be played by activated carbon on these kinds of sites. And the original rule of thumb that you can't put enough carbon in the ground to absorb all the mass out on these free phase sites, I mean, that's an absolutely true statement. But we're missing the point. The point really is that we don't care about the absorption capacity. What we care about is that there's a relationship between this total stage, this total surface area of the carbon that we put in the ground, and the mass removal rate. So we can actually use this to design achieving some sort of a cleanup standard just based upon the amount of carbon that we put in the ground. And it's based on a kinetic design rather than an absorption design. This was one of the really important things that came out of the bench test that was done here at RPI using diesel fuel, was this concept that there is this relationship between the total surface area of the stage upon which the degradation is occurring, the activated carbon, and the rate at which the removal is taking place, the rate of degradation. So I would say that activated carbon-based products like RPI's Boss-200 product they've got a really powerful role that they can play on these LNAPL sites. So here's just a quick summary of some of the places where these LNAPL sites where we've actually applied Boss-200, and also the one site where we applied the technology that I showed you the slides from. So you can see that on that particular site, the one that I showed the slides on, out of 20 wells as of September 2019, and that was about 2 years after the treatment. And the design was based on achieving elimination of LNAPL and achieving the goals on the site in 18 to 24 months. So out of 20 wells, at this point we had 2 that still had measurable LNAPL. 11 out of that 20 that originally started with free product, the benzene in there was below the MCL, and this was a condensate site, and the condensate in Texas is pretty rich in benzene, so it's not a trace level contaminant. It's fairly high. 6 of the, as of September 2019, 6 of them, the data still suggested that we had submerged NAPL. Since that time, there's been an improvement at the site. As you might imagine, we're down to just literally 2 wells, one of which was in the center of the old source area, which access was really difficult to, and one other one that had a trace. The rest of them, there's been no detectable NAPL for a long time. So you can see we've treated roughly 50 LNAPL sites, from spanning crude oil through mineral spirits, condensate, paint thinners. At this point in time, over 60% of them are closed. There was a site in Denmark also that was gasoline. We had started out with 1 to 5 feet of petrol and monitor wells. It took a longer period of time, but approximately 5 years from the pilot, the site received an NFA in 2018. So what's the point? The point is that activated carbon has a really powerful role that it can play on these LNAPL sites. And I know that many people in the industry felt like, well, activated carbon doesn't really have a good application here because you physically can't put enough carbon in the ground to absorb all that mass that's there. And that's a correct statement, but we're missing the point. There's a kinetic feature here that needs to be included. So some of the other things that are really important with activated carbon in terms of its properties are it's a conductor. Well, so what? So this slide is just a rough animation of that characteristic of it being a conductor. So those little sparkly things are electrons moving along the carbon structure. And this particular slide is trying to crudely depict reductive dechlorination. So electrons are coming in, being conducted by the carbon to, and this particular material is reminiscent of our BOS 100 product, which is activated carbon where the inner pore structure has been impregnated with metallic iron. So here's the iron inside the pore structure of the carbon. Electrons come in, and then reductive dechlorination takes place. These little green balls were the chlorine on, this is a TCE molecule. So we're degrading that, and it's the conductivity of the carbon to shuttle electrons around is really important. So we'll look at that one more time. This concept has been used not just by RPI for degradation of chlorinated solvents with our BOS 100 product, but there have been other applications of this. For example, Professor Finneran at Clemson University took advantage of this very same feature, the fact that electrons can be shuttled by the activated carbon to degrade things that are actually absorbed in the carbon. And he did some work with explosives, RDX, for example. And RDX was actually, that had been absorbed on the carbon, was degraded through a biological feature that generated electrons. So you had electron donors present that were fermenting, generating electrons. And then those electrons were being shuttled by the activated carbon to the point where they were needed. That same concept has been exploited by RPI with its CAT 100 product, where we've now married the original abiotic mechanism of degradation of chlorinated solvents by the metallic iron that we've impregnated inside activated carbon in our BOS 100 product. We've now married that with the biological. And you can see that as we generate electrons, they can be shuttled to the point where the iron is located inside the material. And the consequence of that is that we protect the iron. If you had asked me a question 5-10 years ago of, so how long does the iron last in BOS 100? My answer would have been, it lasts as long as the iron, because the iron is oxidized through this process. Now though, when you marry it in just the right way with biological, you can use outside electron donors. And we've used starch for this purpose on many sites. And the fermentation of the starch generates electrons, which then can be shuttled by the carbon to the iron deposits inside the pore structure and protect the iron. So, I mean, the CAT 100 is the technology out there, and it's because the iron is taking on a true catalytic role. It's life. It's being protected against oxidation. So these are really cool features. Activated carbon is just an amazing material. With that, I think we're at the end of the presentation, and I'd like to go ahead and open it up to questions.
All right, thanks, Scott. We did have some questions come in while you were speaking. Go ahead and fire some of those off to you, and we'll continue. I think we have an hour time slot allotted here, so we'll be here for a little while. So feel free to submit your question now that Scott has wrapped up. So I guess start things off, Scott. You had mentioned the lab kind of early on in the presentation, and so can you just briefly provide some information about the capabilities of the lab and what someone needs to do if they want to submit samples?
Oh yeah, absolutely. We have a really pretty large laboratory here at corporate RPI in Golden, Colorado. Last count, I don't know, we probably have 7, 8 GC mass spectrometers, ion chromatographs, headspace, ECD instruments. We've got a lot of analytical instrumentation here. Basically, RPI has been, as everyone probably knows, pretty much focused on organic contaminants throughout its history to date. And so the laboratory is really focused on those kinds of analyses. So the standard fare of 8260, for the most part, we use a lot of GC mass spec instrumentation for our analytical work. So 8260 for VOCs, 8270 for semi-volatiles, PCBs, pesticides, hydrocarbons. We can analyze for all of those things. And the whole idea of the laboratory was to support these RDC efforts that I alluded to very early on in the presentation. So the first step on a lot of these sites is to go out and really get a much better handle on what the distribution of contaminant mass is, both aerially and vertically. And I put this in the very beginning of the presentation because I think it's just so critically important. I realized that the standard nature and extent type characterizations that are done and have been done for decades throughout the industry are really important for the role that they play. And that is to just try to get your arms around the nature and the extent of contamination on a site. But when it comes to in situ remediation, like I pointed out very early on, it's very surgical. And so you really need to have detailed analytical information to be able to track the distribution of contamination vertically and aerially. So RPI we think this is so important, this kind of data, that from the very beginning we've always offered access to our laboratory at no cost. So we typically like to go out on a site and take additional soil samples and groundwater samples, and this is called RDC, or remedial design characterization. So in a couple of days of work out on a site with a direct push rig, we can generate literally hundreds of soil samples, which then are submitted to RPI. We do the analytical work here and share all of the data among the stakeholders on any site, and there's no cost associated with that.
Great. Thank you. And I guess if you're interested in submitting samples, you can reach out to me, you can reach out to Bob. You have his email address. You've got Scott's right there. There's a chain of custody link that's on the Trap and Treat website that's got some information if you are considering sending some samples into RPI. So thanks, Scott.
Also, something else I'd like to say real quick before we go on to the next. It was something I kind of overlooked during the presentation, and that is, I talked about bioavailability, and I didn't get into a lot of detail there. But some of these, some of the work that I alluded to, like Professor Finneran's at Clemson University, and also another gentleman, Derek Lovely, Professor Lovely, has some pivotal work out there that really does speak to the bioavailability of things that are adsorbed to carbon and how some of those things happen. And I've got copies of a lot of these papers. So anyone who might be interested in seeing some of that independent research to see how this concept that I sort of described with crude animation of electrons being shuttled by the activated carbon, just email me or give me a call, let me know, and I can share some of that research with you and just share the papers with you. It's not a problem. Some really interesting stuff.
Cool. Thanks, Scott. The next questions, I'll just kind of lump them together. They're both sort of contaminant specific, sort of. One is, relates to DNAPL. You had spent some time talking about the site in Texas and LNAPL. And so one is for treatment options for DNAPL, and then second one would be treatment of 1,4-dioxane.
Okay. Quite different topics.
Right. So, I just lumped them together for you.
That's all right. That's fine. So I don't know which of the two is easier. I'll start with the DNAPL. As I said earlier in the presentation, people over the years have asked me how long BOSS 100 lasts. BOSS 100 is our product that we have. It's granular activated carbon with elemental iron impregnated into the microporous structure of the carbon. The answer to that question is it lasts as long as the iron lasts, because we all know that through the process of reductive dechlorination, the iron, the metallic iron itself, is oxidized, and those electrons are then, and it's oxidized through the reductive dechlorination process, the degradation of these materials. And so, and at this point, it's been a number of years ago. For a long time, I pretty much knew that there would be some synergy between biological ERD, enhanced reductive dechlorination, and the BOSS 100 product. So we started doing work along those lines, and the result of that was our CAT 100 product. And it's now been in the marketplace for a number of years. It's been applied to sites where, I mean, we have literally DNAPL sites. So this was really a product that was originally designed for DNAPL. And the result, as I alluded to in the presentation, of this combination is that the microbes, and you need more microbes than just the microbes that degrade chlorinated solvents. You need microbes in there that can degrade the donor, the electron donor, the hydrogen donor, if you will. Those are kind of synonymous concepts. In this case, the starch. And it's at least our position here that a lot of the bugs that are out there, like the DHC and so on, that can degrade chlorinated solvents, aren't all that adept at degrading things like starch. So we have a set of bugs in the CAT 100 that's their sole purpose in life, is to degrade those complex carbohydrates and knock them down to smaller pieces that can then be beneficially utilized by some of these other organisms. So the net effect of all that is, once we get the bio going, then the bio starts to generate these electrons, which then can be shuttled by the carbon, and we can preserve the iron. So that's the product that we really designed around going after DNAPL sites. And we've applied it to sites that were so heavily impacted that during the RDC sampling, literally free product, one of them was a carbon tet site, ran out of the sample sleeve. And we've had a lot of really good success. One of the classic projects that we were involved in, and I just call it the contaminant soup project, literally had hydrocarbons, ketones, esters, chlorinated solvents. There was this broad spectrum of different contaminants present in the groundwater. And frankly, at that time, this is several years ago at this point, we really didn't know how the CAT technology would function in that kind of an environment where we were looking at degradation of things like ethyl ether and TCE and benzene, acetonitrile. It was just a really convoluted mix. But we've actually successfully, it's under managed closure, so I can't say it's totally closed. But the site was treated using the CAT technology, and we were able to actually see not just chlorinated solvents, but also these other contaminants being degraded as well. So it's a very powerful technology, and this idea of electron transport by carbon is a really powerful thing. Now, coming back to 1,4-dioxin. 1,4-dioxin is a different kind of animal. But we're going to have to switch topics now and talk about BOSS 200, because BOSS 200 was really the product that was engineered and designed towards degradation of petroleum hydrocarbons. And that's really the technology that was being utilized, although it was enhanced with some donors on our diesel bench. It turns out the blends of organisms, and we've been working with our bug vendor for a long time to enhance the ability to degrade benzene, oxygenates like MTBE, tertiary butyl alcohol, and so on. So we actually had them do some testing with our consortia that is utilized for the hydrocarbon generation or degradation, sorry. And we tested that with 1,4-dioxin. And there are bugs in our mix that will degrade 1,4-dioxin. So we're in the process now of, and I don't know whether we'll manage to get it all put together this year. We've done some preliminary testing, but we're going to put a bench test together with the enhanced BOSS 200 technology to see how successful we can be on the 1,4-dioxin. The one thing about 1,4-dioxin that doesn't work in our favor is it's got a very low heat of absorption, And everyone knows this in the industry, it doesn't absorb very well to carbon. So we can't get the same kind of right out of the gate effect due to absorption to drop concentrations, not the same magnitude that we can get with things like TCE, for example. But we have, based on preliminary testing, we're pretty confident that we can not only absorb the 1,4-dioxane, but we can degrade it as well. One of the difficulties associated with running this bench test is the degradation byproducts of 1,4-dioxane are not just commercially available off the shelf from chemical suppliers. One of them is available out of China, but as you can imagine, it's certainly, given the current situation with China, it's difficult to get anything out of China and get it successfully imported here. So what we've had to do is actually synthesize a couple of these byproducts, and we're in the process of doing that now so that we can calibrate for the degradation byproducts to not only demonstrate absorption but true degradation. So we don't have something out there that we're ready to market, but I think we're going to have something early next year to address that contaminant.
Great. We have a couple more questions. I'll just make one comment to the group here. I've gotten multiple questions on application techniques, and so we are starting actually next week. We're going to be talking about chlorinated solvent remediation, but that will be part of that presentation. Will be the actual application. Same thing the following week, which is going to be petroleum hydrocarbon. That's going to focus on BOSS 200. Scott mentioned I'll actually be giving that one. And then we've got fractured bedrock, and then we've got kind of challenging geology to wrap up the series. So we're gonna shelve those questions for now. And if you have any immediate questions, please feel free to reach out to us, but those will be the focus point. We'll be focusing on the application techniques in subsequent webinars. So Scott, we've got two more here. So I'm gonna, first one here, it says, does the zero order imply a rate irrespective of the groundwater concentration because the activity takes place in the carbon matrix that has a relatively similar concentration since it's saturated until we reduce the source?
I'm so glad that someone asked that question, because that was one of the pieces that I kind of skipped over. And that's the importance of that zero order kinetics that is displayed on that graph and the relationship between the surface area of the carbon. RPI certainly strongly believes that that this is the case. And the surface area, it's like a massive stage. So the degradation is being played out on this stage. The larger the stage, the more rapid the degradation rate. From the graph in the bench study that we did on the diesel test, I mean, we extrapolated a kinetic rate from that data. We've applied that same rate, and we extrapolated a very comparable rate from the site that I was talking about in Texas for the condensate that was being treated down there. But in any case, so that opens up a whole new way of looking at design. And I neglected to really explain this. Normally, people tend to think about using activated carbon in the design for remediation based upon absorption capacity. How much carbon do I have to put in the ground to reduce my benzene concentration from where it is now to 5 ppb so that I could start closure monitoring on my site? The data from the bench test, the diesel bench test, really pointed us in a totally different direction. It now said, wait a minute, let's talk about kinetic design. Let's use the kinetics, the rate of degradation, and how that's related back to the surface area of the carbon. So it opens up a whole new dimension and a whole new way to go about addressing sites. And we've employed this on more than one LNAPL site to date, very successfully. So what it allows us to do is to really look at, through a discussion with you, the consultant or the property owner, to say, okay, so this is what your site looks like today, and what kind of a timeline can we look at? So we can back into, based upon a timeline, to eliminate LNAPL, measurable LNAPL, for example, on a site, on a diesel site is a good example. And then use that timeline to then take advantage of the kinetic design to back into an amount of carbon that I would, or Boss 200 in this case, that I would actually need to put on the site in order to achieve that. So industry is not wrong with their comment to me a long time ago that said a lot of these Elm apple sites, there's so much mass in the ground, you can't put enough carbon in the ground. They're right. That was the whole idea of trying to measure absorption capacity. And even though we measured a much higher absorption capacity than the rule of thumb in industry missed the point. The real point here is the fact that there is a relationship between the amount of carbon in the surface area, the stage, the size of the stage that the degradation is being played out on. And we can use that to an advantage. So the use of activated carbon when it comes to these Elm apple sites and natural source zone depletion, I just didn't spend enough time on this. There's a huge role for products like Boss 200 to be played in that industry. We can really shorten the timeline, as was shown by that one slide where we had 7 times the mass removal rate on our site down in Texas versus what would have been predicted based upon the mnemonic graph that came from the ITRC document on Elm apple. There's a huge role that can be played. And in general, one of the things I'd leave everyone here with is activated carbon is such a cool material, and it's so powerful. There's so many different ways you can approach a design. It just needs to be used a lot more extensively in the industry for remediation, and I'm sure it will be over time.
All right, Scott. Last question. This is one of my favorites that we get from time to time. It says, it's well written, so I'll read it verbatim. Can you describe a quote crash and burn unquote failure of your technology? When has it not worked and under what conditions?
I can. We've been, like I said in the very beginning, we've been putting carbon in the ground for 19 years. And when we first started putting carbon in the ground, I mean, frankly, we didn't know what we were doing, and we were just learning as we went. We had no idea what would happen when we did the injections. So over the years, I mean, we from time to time have failures. Most of the failures that we've had are related to distribution, because everyone knows this is a contact sport. And when you start injecting slurries in the ground, and slurries are not easy to inject. Solutions are great, so like persulfate solutions, they're really easy to inject. You can do it with almost any kind of equipment. You don't have to have special techniques. Some of these other webinars are going to really speak in detail about those techniques, because all of our products are slurries, and injection of slurries is not easy. And so distribution is really important. And you would think that some of the toughest lithologies would be things like fat clays, heavy clays, interbedded silts and sands and clays and so on. I can tell you that over the years, in the beginning, we got fed nothing but those kind of sites because they were kind of tough. We've had really good success on those. The ones that we kind of struggled with were sand. And you'd think sand would be easy to inject in, but if you start thinking about slurries, an injection of slurries, sand does exactly what it does in a monitor well. It's sand pack. So you inject it into the subsurface, the water moves through the sand very easily. What doesn't move through the sand real easily are the suspended solids in your slurry. It filters it out. And so we had to develop special techniques for that. Every site is unique. And the first day or so on any site is really kind of dedicated to figuring out how the subsurface is going to respond to these injections. How much difficulty is surfacing going to be? So some of the sites, just within the last couple of years, we're working on it currently, but there's a problematic site in the Rust Belt and it is a chlorinated solvent site, and it's in sand. And the techniques that we had developed a long time ago at Vandenberg Air Force Base to really deal with sand, the first initial injections that were done there didn't perform well. And when we went back and started looking at the distribution of material in the subsurface, frankly, it was horrible. So we're in the process now of looking at what can be done to try to get a better distribution in the sand. So absolutely, we're not perfect, and we've had failures on sites where things don't perform as well as we think they should based upon all the design calculations. From our website, you can tell that, I mean, we also have a lot of successes. We've been very successful at closing sites. I'd be hard pressed to tell you what percentage of sites that we have are unsuccessful. Part of that just has to do with how do you define that. If our target was to reduce everything to below 1 part per billion and absolutely close the site, I mean, we treat a lot of sites where, I mean, that's not even a realistic goal because it's a PRB, for example, or you've got a lot of mass underneath a building that's just going to bleed contamination into perpetuity. So again, every site is unique. Distribution probably has been at the heart of probably 90% or more of the projects where we've had less than stellar results or less than the results that we designed for. That's probably the biggest thing. And I guess one of the things that I would leave you with on that idea would be the contractors that are used to install these products are probably the most important decision you're going to make when it comes to in situ remediation, particularly if you're injecting slurries. So because of that, RPI a long time ago drew a line in the sand, and we won't let just anybody inject our products, as people in the industry know. There are very specific companies like AST and other companies that are identified on our website that are part of the RPI group, if you will, and they're the ones that have been trained on how to actually put these things in the ground to make sure that we're going to have the success that we've designed for. The other piece to the puzzle that's really important is it's not just the injection contractor and making sure they have the right kind of equipment and that they have the right kind of techniques to put these things in the ground to achieve what's necessary in order to get good results. The other piece to the puzzle was where I started. It's knowing the distribution of contamination, because if I go out there and if I don't know where there's pockets of really high contamination, it doesn't matter what I did. It doesn't matter how good the product is. I'm not going to be successful. So that thing I mentioned, RDC, that remedial design characterization, that's something that almost across the board we insist on doing that, going through that exercise on sites to really develop the distribution of mass, contaminant mass, both vertically and aerially on a site, because that supports the entire design for the treatment.
Well, thanks, Scott. Yeah, those are actually two things that I mentioned in my presentation that I'll be giving in a few weeks. Is it's really comes down to understanding where the mass is and distribution, and it's usually one of those two things that are gonna sink a site. And so we're gonna spend some time on those topics specifically as we go through the rest of the presentations in the series and focus on the successes that we have had in sand. Scott mentioned sand can be a challenge. We've also had a lot of success in sand. It can be tough for slurries, but we've figured that out over the years. Same things on the other side of the spectrum with clays and silts to glacial till, weathered bedrock, and then bedrock. So we're going to actually touch base on all of that in the rest of the series here. And so I guess before we wrap up, if there's something that interested you today, or if you would like a one-on-one presentation on something specific, please reach out to us. We can make that happen. If you've got a site and you want to evaluate it, but you want to learn more about BOSS 100 specifically, please reach out. We can go ahead and set up something one-on-one or with your office. So I guess I'll leave it there. Thank you very much for attending. I know, Scott, if you have any final words before we sign off.
No, just to thank everyone for their time. I know you're busy, so it's certainly appreciated. And just like Mike said, if you have any questions, if you'd like to get copies of some of the papers that I talked about from Derek Lovely, Professor Lovely, or Finneran, or some of the other resources that we have, I'm happy to share that with people. So please, everyone, have a wonderful day, and we look forward to hearing from you.
All right. Thank you, Scott. Take care, everyone.
Okay.